I am going to talk about using GPUs, and there will be a general part, and there will be one part focusing on how you allocate the GPUs at the various systems in Sweden, at least a focus on the NAISS system and a few others. And then a little bit about how to deploy them on those systems. So, okay. So when you use GPUs, what is GPU acceleration? How do I enable GPUs? And how do I deploy them at the NAISS centers and at these three local centers? And there is some difference between the centers, but it's not hugely. It's mainly that they have different GPUs and you ask for them in a slightly different way. But we will go into that. So let's start by looking a little bit at a GPU and how to compare it to a pure CPU. And this here, it shows a CPU architecture. And this is one of the CPU nodes on UPPMAX. It's an AMD Zen 4 node. This isn't very important, but you can see here it's divided into NUMA nodes, 2 sockets, and where half of the cores sit on each of them. This type of node has 256 cores, and each of these cores have some cache memory, and there's also shared memory, some shared memory within the NUMA node, and some you can access easier. I mean, even if it's on the other NUMA node, it's still faster to access than it would be to access on a different node, but it's slower than if it's within the same socket. And you can see each of these cores have various types of cache. So if you can fit a calculation within the lowest L1 cache, then it is faster. And then it slowly gets less fast the further out you go, but it also gets a larger amount of memory. But this isn't very important. This is just to show you how a CPU could look and how they typically look. And they also connected to local disk and then out to the network through a controller.
One question here. Does this mean that the threading can only use up to half of the node?
No, you can do threading on the whole node.
Okay.
It is connected, so you can do that. I believe that if you do benchmarking, probably it will be ever so slightly slower, but there's no problem with it. I mean, you can address all the memory from both. It's just a bit slow. So this was the CPU. I'm going to mute this. Just one moment. I need to mute the NAISS chat because it keeps popping up stuff. I'm going to close it. Okay. I will continue. So the GPU card would look something like this, and this is something that is similar to L40Ss. It's an Ada Lovelace, and that is one of the. There are some minor differences between them, but an L40S, which I believe is what is now on Pelle, and it's also some of those that we have many of on UPPMAX. So it's a type of GPU. And I'm going to see if I can zoom on this. Can somewhat. And you can see it is different to a GPU. There are many more cores, smaller cores. So here there are 256 cores, but here there are many more cores. And it has both CUDA cores, and it has tensor cores. And I believe this one also has matrix cores. No, it's not matrix cores, that's the name of the GPUs. It has the raster graphics ones, what are they called? That disappeared from my brain, but it's some ray tracing cores they have. So it has 3 types of cores, and they can be used for lesser and lesser. Oh, my brain is not working right now. But I mean, it has to do with the precision. On the regular CUDA cores, you can normally do either single precision or double precision, depending on the type of GPU. But on the tensor cores, it's often half precision or down. It can even be down to quarter precision. And you can, of course, simulate single or double precision with lower precision, but it is dependent on what type of calculations you want to do. So if you have something where it doesn't matter that it's half precision, for instance, then you would run it on the tensor core. So that is often what you do in machine learning. It's like this. This is one of those that you see here that you go in. It's there are 12 here of these graphic processing clusters, and they each have CUDA cores and tensor cores. So it's simply it's built up in a different way than the CPUs. Many smaller cores that can do much less each. But if it's really is massively parallel, then that's good. Then you can really run on it. Yeah, and as I said, GPUs are connected to a CPU, and you can run on both of them. I believe that the new Arrhenius cluster, I don't remember what type of CPUs they are getting for the GPUs, but I believe that Erik Lindahl said that they will be reasonably good CPUs. Does any of you remember what he said?
ARM on the GPU nodes.
It was ARM. Yes, that's true. Yeah, and that can be discussed, of course. If you want ARM CPUs. I don't know. I mean, I might have taken something different, but I'm sure there's a good reason for them. People who know more than me probably knows if they are efficient or not. This is as an example of how it would look. So these L40S GPUs, they are connected. And in this case, there are 2 L40S GPU cards. So there is one connected to each socket. And that means that if you are allocating a GPU on that, then you are also allocating the CPU, because no one can really run on that. It's going to interfere massively if they did that. So you get both. And if you want the whole node, then you can allocate that. But this is something that differs between centers. Some let you allocate half nodes, some only full nodes. And it also depends on how many cards are on each of them. And Kebnekaise has many different types, and so does some of the others. I believe Pelle has L40S, and it has something else also, I think. The new UPPMAX cluster. But it's mainly the L40Ss that you will be running on there. Yeah. So you can look at the CPU and GPU performance with 2 quantities. There's both latency and there's throughput. Latency is the time spent in a sole computation, and throughput is the number of computation you can perform in parallel. And if you look at it that way, you would say that CPUs has low latency. It can do fast computation, but it has low throughput because it can only do few computations simultaneously. This was while many cores, it's not many compared to how many there are on a GPU. And this image sort of shows that. A CPU might be a road that only has a few racing cars that drive, but a GPU has a large road, but there are many small cars that drive on each of them. So massively parallel, then it's GPUs. Yes, not every program is suitable for GPU acceleration. GPUs process simple functions rapid, and you should do repetitive high parallel computing tasks. And as you probably know, GPUs were made for rendering high resolution images and video concurrently and fast. But since you can perform multiple operations on multiple sets of data, they are also often used for non-graphical tasks. Common use are machine learning and scientific computations, where you can take advantage of the massive parallelism. It is important to note that many R packages are not CUDA aware, but some are written specifically with GPUs in mind. And now when I say CUDA aware, then maybe you think that, what about Dardel? Dardel does not have NVIDIA GPUs, and there are also some other centers, including Kebnekaise, which has some AMD GPUs. And if you have AMD GPUs, you can't run a CUDA program directly. You have to use something like HIP, but you can translate them. Many Julia packages are also not CUDA aware, but there is a CUDA.jl package that is the main programming interface for working with NVIDIA GPUs. Matlab has support for GPUs, but you will need to write functions that support GPU executions. And many of the functions in Matlab actually can run automatically on a GPU if you supply a GPU array data element. You require to have the parallel computing toolbox. And I have linked to some information at MathWorks here about that. So one of the most common uses for GPUs with R, there's an R missing, and Julia is for machine learning or deep learning. And we'll talk about that later. So now we know a bit about what is the difference between CPUs and GPUs. How then do you access the GPUs at the various high-performance computing centers in Sweden? Well, you can't really use the login nodes for it, because either there are no GPUs or you cannot access them for computation. And besides, there's this rule against running heavy or long jobs on the login node because it slows it down for everyone. So if you want to use them, you need to either launch an interactive job or submit a batch job. And the interactive job or the batch job, it can also be through the open on demand system. Because when you start that, then you are actually running a job, and then you can work interactively. And you can also submit from inside of, for instance, Matlab. So C3SE, they have Albis, which is meant for GPU jobs. There's no node sharing on multi-node jobs. But if you request one node, it doesn't mean you can access the full node, but it will be allocated. And you need to add this to your batch script. And they have a number of different nodes. And I think the ones you would usually use are the T4s. And those that are up to 8 cards on each node of. That means that you could put type, you would put T4, and then you could put from 1 to 8 here. At NSC, then you would also have some T40 GPUs. And since they only have this one type of GPUs, you don't need to tell which type it is you want. But you do have to tell it that you want also to book this whole socket that it's sitting on. And then how many GPUs per task. And this is probably 1, because I believe there are 1 on the nodes. Dardel has the AMD GPUs. It's a Cray also, so it's in general quite different to the other systems. And this is how you are asking for a GPU at Dardel. There they do it by giving a partition. They have the GPU partition. You should generally always use give a partition in order to start jobs at Dardel. And again, remember, this is AMD GPUs. You can use CUDA packages, CUDA packages. You need to use HIP, or you need to use something that is written specifically for AMD GPUs. And there are packages for that, for at least R, and I believe also Julia. I don't know what the status is for Matlab actually here. I don't know if, does any of you know that? Yeah, it was.
Sorry, what was the question?
The question was if what the status was for AMD GPUs in Matlab, if you can run jobs on that. Has Matlab written something that works, so it works for AMD GPUs, or is it only for NVIDIA GPUs?
I don't know, but I would be a bit surprised if the GPUs are not working on Dardel with Matlab, but it might be so.
I don't know. I made a short attempt yesterday to check for it, and I couldn't find anything.
No, okay.
But it might just mean that it works, or it might mean that it doesn't. I would need to ask, and we can do that when we perhaps have a meeting with it. Okay, I will continue. So if you are at UPPMAX, if it's Rackham, there are no GPUs, and you need to use Snowy. If you are using Pelle, then Pelle has GPUs, and I guess you would use L40Ss, or I don't know if the H100s are more expensive to allocate. At least that's the case for us at SPC2N. But in any case, you tell it that you want to run in the GPU partition, and then you say what kind of GPU and how many of them. And it depends. If it's L40Ss, you can have up to 10. If it's H100s, you can have up to 2. HPC2N has many different types of GPUs, and this are the number of cards. To access them, you add this line to your batch system. GPU SBatch minus GPUs equal and the number of GPU cards, which is one of these. If you don't tell it what type of GPU you want, then you cannot give more than 2, because as you can see, there are 2 of any kind. And if you ask for 4 and you get the A100s assigned, then it's going to fail. So you either ask for no more than 2, or you tell it what type you want. And type is, of course, these. It's just written with lowercase. And you can see that at SPC2N's guide, this link. LUNARC has A100s and A40s, but the A40s are only meant to be used for the interactive graphics work on the on-demand. So you should only submit to the A100s. And again, you are telling what partition you want to run in, and then you are telling how many. And I believe the option can only be one. Or maybe it's two also. Yeah, that it depends. These ones have one or two, but I believe these have only one. Okay. So let's go ahead and look at actually how would it look inside the script. And if it's for R, yes, you have seen a batch script before. And at NSC, this is the small block that we just showed before, that you then put inside your batch script. And then what you do is you load a module of R that actually can use GPUs. And then you run a script that uses GPUs. And it's the same at all of them. You need to simply make sure that you put this small block of text into your batch script, that you load a module that is GPU aware or whatever. Here, this is for the AMD GPUs at the PDC. And I'm not going to go through all of these because you simply you can look at them yourself. But at HPC2N, you just need to load the CUDA module, and it's the same for LUNAR. And then, of course, use an R package you have installed, or which are from CRAN and which uses GPUs in the script, of course. So for Matlab, to use GPUs with Matlab, you can do it from inside Matlab, or you can do it in a batch script. In any case, in order to use them, you must ask for them, just like otherwise. And it's inside GPUs. You add them to additional properties, like you do with other things when you're asking for which project to run in, how long to run in. So you set it with c.additionalproperties.gpu card. And c additional properties, GPUs per node. And this is how you add them to use in a batch script also. But you can do this inside of Matlab. So you simply set that and then you start a job from inside Matlab. And here it is shown how you do that at the various centers. I'm not going to go into detail of this. But in any case, you are asking for these additional properties at these four centers. At PDC and C3SC, you don't set additional properties. Instead, you start an interactive session on the GPU partition, and then you log in to that node and load Matlab there and start it. It's done in slightly different ways at those two, but it's that way in both of them. One thing to remember is if you have added GPUs to additional properties and saved it, it will be the next time you start Matlab. So you need to erase it again with this command here. Just give the same additional properties, but with an empty string. You can always do c.additionalproperties to see what you have saved. So if you're using it in batch scripts, you simply do it like you do in any other batch script. You ask for the GPUs, and then you run a GPU Matlab script. And there is a little difference between centers in that, so there's no reason to talk about that further. For Julia, if you want to use NVIDIA GPUs with Julia, then you need to load a CUDA toolkit module at UPPMAX, HPC2N, and LUNARC. I believe, I'm not sure at UPPMAX actually because it has changed. On PDC, you need to load the ROCm toolkit instead to use the AMD GPU package in Julia. And at the NSC, there's also a CUDA package, but you need to add it yourself. So, but this is how it's done at the various centers. And you are at HPC2N, then you do it this way. So you load the Julia module, and then you load a CUDA module, and then start Julia, and then you install this CUDA Julia package. When you have this setting up, you are able to use GPUs on the cluster with Julia. And there is a simple example for computing a matrix multiplication. And it's this one here. And when I have, in a very short moment, finished this presentation, I would like you to try and run this. Yeah, the HPC2N on NSC or where you have your account. And this should work. You just need to change it to your project. You can use it, the course project, which for HPC2N is HPC2N 2025 minus 151. And for NSC, it's NAISS 2025 minus 22 minus 934. But you can find those in this introduction up here about the sentence. And if you are running on the AMD GPUs, then there is a slightly different GPU script, because now we are using this drop array instead of as up here, where we are using the CUDA array. So there is not actually a lot of different in Julia, but it's done. There are some differences you need to do in order to make it compute here. And here it's mainly just using block array instead of QA. Okay, so let's do the exercise. Try and run this script. It's listed here. And you can run the simulation twice. And you can compare it between different centers if you want to, but you should try and run it now. And there's an answer to the output here. And you can compare what you get.